Night falls quietly. The world softens, the noise fades, and above you, the sky begins to reveal itself. At first, it's just a handful of stars, then more and more, until the darkness is no longer empty, but alive, filled with countless points of light scattered across the vast black canvas. If you're far from city lights, you might see the Milky Way stretching overhead, a pale river of stars flowing from horizon to horizon. A faint glow, almost like mist, made of billions of distant suns blending into one. It feels full. It feels rich. It feels like the universe is overflowing with light. For most of human history, this was the ultimate truth of the cosmos. Ancient civilizations looked up and saw patterns, stories, constellations woven into a sky that seemed crowded and vibrant. Philosophers imagined a universe filled with celestial spheres, each one packed with stars, planets, and meaning. Even today, standing beneath a clear night sky, it's difficult to escape that same feeling. How could something that looks like this be empty? Your eyes tell you one story, a story of abundance, a universe bursting with stars, galaxies, and glowing clouds of gas, a place where matter seems to be everywhere, layered upon itself in infinite complexity. But there's a quiet problem hiding inside that beauty, a problem so subtle that you would never notice it just by looking. Because what you're seeing isn't the universe. It's your neighborhood. Every star you can see with your naked eye, every single one, is part of our galaxy, the Milky Way. And not even the whole galaxy, just a small local region surrounding our sun. The furthest stars visible without a telescope are only a tiny fraction of the galaxy's full size. To your eyes, they seem scattered across the entire universe, but in reality, they're clustered within a relatively small cosmic distance. It's like standing in your backyard at night, looking at the lights of nearby houses and assuming you're seeing the entire world. But you're not. You're seeing a tiny patch of it, and that patch just happens to be unusually bright. The Milky Way itself contains hundreds of billions of stars, a vast rotating disk of light stretching over 100,000 light-years across. When you see that faint glowing band in the sky, you're looking along the dense plane of this galaxy, where stars are packed more tightly together. It creates the illusion of density, the illusion of fullness. But even here, inside one of the most structured environments in the universe, space is still overwhelmingly vast. The stars that seem close together in the sky are separated by distances so large that light itself takes years, sometimes thousands of years, to travel between them. And beyond the Milky Way, things become far stranger. Because our galaxy is not the universe. It is just one galaxy among hundreds of billions. Each of those galaxies contains billions or even trillions of stars. And when we look deeper into space with powerful telescopes, we begin to see them. Faint smudges of light, spiral shapes, elliptical glows, entire island universes scattered across the darkness. At first glance, this seems to confirm what your eyes suggested all along. The universe is full. Galaxies everywhere, stars beyond counting, light stretching across unimaginable distances. But this is where intuition begins to break down, because seeing something is not the same as understanding how much of it there actually is. Human perception is not built for cosmic scale. It compresses distance. It flattens depth. It turns three-dimensional reality into a two-dimensional image projected onto the sky. Stars that are separated by trillions of miles appear side by side, Galaxies, separated by millions of light years, seem to sit next to each other like scattered grains of dust. Your mind connects the dots, and in doing so, it creates a false sense of closeness, a false sense of density. Imagine holding a handful of glitter in a dark room. You toss it into the air, and for a brief moment it sparkles all around you. Light reflects off each tiny piece, creating the illusion of a dense cloud. But in reality, those particles are separated by empty space, vast gaps between each one. The glitter is not a solid object. It's a sparse collection of points, briefly illuminated. Now imagine that on a cosmic scale. That's what the night sky is, a projection of scattered light, stretched across distances so large that your brain simply cannot process them correctly. And there's another layer to this illusion: brightness. The stars you see are not just nearby, they are also among the brighter ones in our region of the galaxy. Many stars are too dim or too distant to be seen at all. Entire regions of space remain invisible to the naked eye, not because they are empty, but because their light hasn't reached you, or isn't strong enough to be detected. So even within your own galaxy, what you see is heavily filtered, selected, biased. You are not looking at a complete picture. You are looking at a curated version of reality, shaped by distance, brightness, and the limitations of human vision. And yet, despite all these limitations, your mind still tells you the same thing. The universe looks full. But science does something different. It doesn't rely on what feels true. It measures. It calculates. It asks a simple question that changes everything. Not how many stars we can see, but how much space they actually occupy. And that question leads to a very different answer. Because when scientists began to measure the universe, not just observe it, they discovered something deeply unsettling. All those stars, all those galaxies, all that light, they barely fill anything at all. The vast majority of the universe is not made of glowing objects or swirling galaxies. It is not filled with light or matter or structure. It is empty. Not just slightly empty, overwhelmingly empty. So empty that if you could somehow shrink the entire observable universe down to the size of Earth, all the stars within it combined would occupy a volume smaller than a single microscopic particle. And even that comparison doesn't fully capture how extreme the emptiness really is. But standing under the night sky, you would never guess this, because your position in the universe is not random. You are inside a rare region where matter has gathered, where stars formed, where light exists in abundance, a small pocket of structure in an otherwise vast and silent expanse. And from inside that pocket, everything looks crowded. Everything looks alive. Everything looks full. But that is not the truth of the universe as a whole. It is a local illusion, a trick of perspective, a consequence of where you happen to be. And once you begin to understand that, the night sky starts to feel different. The stars no longer seem like evidence of abundance. They begin to feel like exceptions, rare points of light scattered across an ocean of darkness, isolated, distant, fragile. And the question slowly begins to form in your mind. If this is what the universe looks like from one of its brightest regions, what does it look like everywhere else? Because the deeper we look, the more unsettling the answer becomes. The universe looks crowded only because we're standing inside one of its rare, bright pockets. And to understand just how rare that pocket really is, we need to zoom out. Step outside on a clear night, and it feels like you are looking at everything. The sky stretches endlessly in every direction, filled with points of light that seem to mark the edges of existence itself. There is a quiet assumption built into that experience, something so natural we rarely question it. If we can see it, it must be a significant part of reality. If it fills our vision, it must be most of what is out there. But the truth is far more humbling. What you are seeing is not the universe. It is a tiny, local fragment of it. Human vision is not designed to understand cosmic scale. It is built for survival on a small planet under a thin atmosphere, within a narrow range of light. And when we lift our eyes to the stars, that limitation comes with us. We are not observing the universe as it is. We are observing it through a narrow window, one that only reveals what is close enough, bright enough, and aligned just right. The furthest stars you can see with your naked eye are only about a few thousand to perhaps 15,000 light-years away. That may sound enormous, and by human standards it truly is. But the Milky Way galaxy, the system that contains all of those visible stars, is about 100,000 light-years across. This means that even on the clearest night, under the darkest skies, you are seeing only a small fraction of your own galaxy, less than a fifth, and that's being generous. Most of the Milky Way remains completely invisible to you, not because it isn't there, but because its light is too faint, too distant, or blocked by clouds of interstellar dust that scatter and absorb what little light tries to reach you. Entire regions filled with billions of stars lie hidden behind these cosmic veils, unseen by human eyes. So when you look up and feel surrounded by stars, you are not seeing the full structure of your galaxy. You are standing inside a small clearing, surrounded by trees, trying to imagine the size of the forest. And even that analogy falls short. Because the Milky Way itself is only one galaxy, one among hundreds of billions, perhaps even trillions scattered across the observable universe. Each of those galaxies is its own vast system, containing stars, planets, gas, dust, and mysteries of its own. Some are larger than ours, some smaller, but none are rare. Galaxies are the basic building blocks of the cosmos, repeated again and again across unimaginable distances. Yet none of that is visible to your eyes. Without technology, without instruments, without extending your senses beyond their natural limits, you would never know they exist. The universe would appear to you as a dome of nearby stars, with no hint of the immense structures lying far beyond. This is where the illusion becomes dangerous, because your brain takes what you see and builds a model of reality around it. It assumes that what is visible is representative, that what fills your field of view must also fill the universe, that brightness implies abundance. But all of those assumptions are wrong. You are not seeing a fair sample of the cosmos. You are seeing a biased one. A local cluster of stars that happens to be close enough to shine brightly in your sky. A small region where matter has gathered, where gravity has pulled gas and dust together to ignite nuclear fusion and create light. You are inside a structure, looking outward, and mistaking that structure for the whole. It's like standing in your backyard at night, surrounded by a few houses with lights on, and concluding that the entire planet must be just as bright. But step back. Zoom out. Rise above your street, your city, your continent, your planet. Suddenly, the lights begin to thin out. Vast, dark regions appear between cities. Oceans stretch across the globe, covering most of its surface in near total darkness. From space, Earth is not a glowing sphere of uniform brightness. It is mostly dark, with scattered pockets of light. Now take that idea and expand it beyond comprehension, because the same principle applies to the universe. The stars you see are not evenly distributed across space. They are clustered, grouped together by gravity into galaxies, and those galaxies themselves are separated by enormous distances. Between them lies vast emptiness, regions so empty that even light can travel for millions of years without encountering anything at all. But your eyes cannot show you that. They compress everything into a flat image, removing depth, hiding distance, and blending together objects that are separated by unimaginable gaps. Two stars that appear side by side in the sky might be separated by hundreds or thousands light years. A faint smudge of light might be an entire galaxy, billions of stars bound together, sitting millions of light years away. To your perception, it all collapses into a single plane, a beautiful illusion, but an illusion nonetheless. This is where human understanding begins to change. Because at some point, we stopped relying only on our eyes. We began to build tools. The first telescopes were simple, glass lenses that gathered more light than the human eye could capture. But even those early instruments transformed our view of the universe. Stars that were invisible suddenly appeared. Structures that were once faint became clear. The sky began to deepen. What looked empty wasn't. And as telescopes improved, that transformation accelerated. We built larger mirrors, more sensitive detectors, instruments that could see not just visible light, but infrared, ultraviolet, radio waves, X-rays, entire regions of the electromagnetic spectrum that human eyes cannot perceive. Each new window revealed something unexpected. More stars, more galaxies, more structure. It was as if the universe was unfolding layer by layer, each deeper look revealing something previously hidden. Regions of sky that once appeared completely black began to fill with faint, distant objects. The deeper we looked, the more we found. At first, this seemed to reinforce the original intuition. Maybe the universe really was full. Maybe it only appeared empty because our eyes were too limited. But something strange happened as our observations became more precise. The more we measured, the more we realized that seeing more objects did not mean space was becoming crowded. Because with every new discovery came a deeper understanding of scale. Yes, there were more stars than we could see. Yes, there were galaxies far beyond our own, but the distances between them were far greater than we had ever imagined. Telescopes did not just reveal more objects, they revealed how far apart those objects truly were. And that changed everything. Because once you begin to measure distance, the illusion begins to break. The sky is no longer a flat surface filled with evenly spaced lights. It becomes a three-dimensional structure, stretching across billions of light years, where matter is scattered like dust across an almost incomprehensibly large volume. You begin to see that what looked dense is actually sparse. What looked crowded is mostly empty. And what felt infinite is structured in ways that challenge every instinct you have. Scale does something powerful to the human mind. It dismantles intuition. At small scales, our instincts work well. We understand distance, density, and proportion because we live within them every day. But at cosmic scales, those instincts fail completely. The numbers become too large, the distances too vast, the structures too immense. And so we fall back on what we see. But what we see is misleading. Because we are not observing the universe from the outside, we are inside it, inside one galaxy, inside one small region where stars are relatively common, inside a bubble of light surrounded by darkness. And from that position, everything looks brighter, closer, and more crowded than it really is. This is the fundamental limitation of perspective. You cannot understand the true nature of a system if you only observe it from within a dense region of that system. You need distance. You need context. You need a way to step back and see the larger structure. Telescopes gave us that first step. They allowed us to extend our senses beyond our immediate surroundings. They revealed that our galaxy is not the center of the universe, not unique, not even particularly special. It is one of many, drifting through space, part of a vast cosmic network that stretches far beyond anything we can directly perceive. And yet, even with all this knowledge, the illusion persists. Because when you step outside tonight and look up, your eyes will still tell you the same story. A sky full of stars, a universe filled with light, a cosmos that feels dense, alive, and abundant. But now, you know something different. You know that what you are seeing is only a tiny fraction of reality, a local sample, a biased view shaped by proximity and brightness. And beyond that view lies something far more unsettling. A universe where matter is rare, where distance dominates, where emptiness is not the exception, but the rule. So what happens when we stop trusting our eyes and start looking deeper? There is a moment in science when curiosity turns into something deeper. A moment when a simple question, almost a quiet whisper, leads to a discovery that reshapes how we see everything. In the mid-1990s, astronomers decided to ask a question that, on the surface, seemed almost pointless. What would happen if we pointed one of the most powerful telescopes ever built at nothing? Not at a bright star, not at a glowing nebula, not at a nearby galaxy, but at a region of the sky that appeared completely empty. A patch of darkness where, to human eyes, there was absolutely nothing to see. This was not a random choice. It was a deliberate act of curiosity, a test of whether the darkness itself might be hiding something just beyond our perception. And for this experiment, they chose a small, unremarkable area in the constellation Ursa Major. If you were to look at that patch of sky yourself, you would see only blackness. No stars, no visible structure, just a quiet void between the brighter points of light. It was, by all appearances, empty. The region was so small that if you held a grain of sand at arm's length, it would cover roughly the same area in the sky. A tiny speck, insignificant compared to the vast dome above us. And yet, for 10 days, 10 full days, the Hubble Space Telescope stared at that darkness. It did not blink. It did not move. It simply collected light. Photon by photon, second by second, hour after hour, building an image so deep that no human eye could ever replicate it. This was not a snapshot. It was an accumulation, a slow gathering of faint signals from the farthest reaches of the cosmos. Imagine sitting in a completely dark room, staring into a corner where nothing seems to exist, and waiting long enough that even the faintest glimmer of light begins to reveal itself. That is what Hubble was doing. And then, slowly, something began to appear. At first, it was almost nothing, just a few faint smudges, tiny hints of structure emerging from the noise. But as more light accumulated, as more photons arrived from across the universe, those smudges sharpened, they multiplied, they filled the frame. What had once been a blank patch of sky transformed into something extraordinary. Thousands of galaxies. Not stars, galaxies, entire island universes, each containing billions of stars, revealed within a region that had appeared completely empty to the naked eye. Every point of light in that image was not a single star, but a massive structure. Spirals, ellipticals, irregular shapes, some glowing blue with young stars, others glowing red with ancient light. Some were relatively close, their shapes clearly defined. Others were so distant that their light had been traveling for billions of years before finally reaching Hubble's mirror. All of this, hidden inside a speck of darkness. The image became known as the Hubble Deep Field, and when scientists first saw it, the reaction was immediate. Astonishment, because it revealed something profound, something almost impossible to grasp at first. There is no such thing as empty space, at least not in the way we imagine it. Every direction you look, even into the darkest regions of the sky, contains structure. Galaxies layered upon galaxies, stretching back through time, filling the universe with light that is simply too faint for us to see without help. What looked like nothing was actually everything. And this discovery changed the way we think about the cosmos, because it suggested something deeply counterintuitive. If a tiny patch of sky, so small it could be covered by a grain of sand, contains thousands of galaxies, then how many galaxies must exist across the entire sky? The answer is staggering. Hundreds of billions, possibly trillions. Each one a vast system of stars, planets, and cosmic events unfolding over billions of years. Suddenly, the universe no longer felt empty. It felt crowded, overwhelmingly so. Wherever you look, there are galaxies. Behind every point of darkness lies another layer of structure, another cluster of stars, another piece of the cosmic story waiting to be seen. It is a powerful reversal. Just moments ago, we were beginning to accept that the universe might be mostly empty, that what we see is only a small, local illusion. But now, with this single observation, that idea seems to collapse. Maybe the universe really is full. Maybe it is filled with galaxies in every direction, stacked across unimaginable distances, creating a richness that our eyes simply cannot detect. And it's not just the Hubble Deep Field. Astronomers repeated the experiment, pointing Hubble at other, seemingly empty regions of the sky. Each time, the result was the same. Darkness gave way to structure. Blank space revealed hidden galaxies. The universe, it seemed, was saturated with matter. No matter where you look, there is something there. Even the voids are not truly empty. This realization carries a kind of quiet comfort. It suggests that the universe is not a cold, barren place, but one filled with structure, with complexity, with countless systems evolving over time. It reinforces the idea that we are part of a vast and active cosmos, not isolated within a lonely expanse. But there is a subtle problem hiding beneath this conclusion. A problem that only appears when we stop looking at images and start thinking about what they actually represent. Because the Hubble Deep Field does not show galaxies packed together in space. It shows galaxies spread out across enormous distances. What you are seeing in that image is not a dense cluster of objects sitting side by side. It is a layered view through the universe. Each galaxy is located at a different distance, often separated by millions or even billions of light years from its neighbors. The image compresses all of that depth into a single flat frame. It makes the universe look crowded. But in reality, those galaxies are not close to each other at all. They are scattered across vast stretches of space, separated by enormous voids that remain invisible in the image. This is the same illusion we encountered earlier, but on a much larger scale. Your eyes compress the night sky into a flat surface. Hubble compresses the deep universe into a flat image. In both cases, depth is hidden, distance is concealed, and density is misrepresented. The more you look, the more structure you see. But that does not mean space is becoming full. It only means your ability to detect faint light is improving. This is the paradox of observation. Seeing more does not necessarily mean there is more. It simply means you are revealing what was already there, spread thinly across an enormous volume. And this is where the story begins to shift again. Because once scientists realized how many galaxies exist, they asked a different question. Not how many, but how much. How much space do all these galaxies actually occupy? How dense is the universe, really? And when they began to answer that question, the result was not comforting. It was something far more unsettling. Because even with trillions of galaxies, the universe is still almost completely empty. The Hubble Deep Field did not prove that the universe is full. It only showed that our perception of emptiness was incomplete. It revealed hidden structure, but it did not change the underlying reality of scale. If anything, it made that reality even more extreme. Because now we knew that all of this structure, all these galaxies, all these stars, exists within a universe so vast that even trillions of them barely make a difference. And that realization leads us to the next step, to move beyond images, beyond observation, into something more precise, more unforgiving. Measurement. Because only when we measure the universe do we begin to understand just how empty it truly is. And yet, that discovery didn't prove the universe was full. It only proved that light can fool you in a different way. The images are beautiful. Galaxies scattered across the darkness, light stretching across billions of years, structures layered upon structures, as if the universe were endlessly full. But there comes a moment in science when beauty is no longer enough. A moment when we stop looking and start counting. Because seeing galaxies is one thing, understanding how much of the universe they actually fill is something very different. So let's do something simple. Let's take everything we've discovered so far, all the stars, all the galaxies, all the glowing structures revealed by telescopes, and ask a question that sounds almost innocent. How much space do they really take up? To answer that, we first need to understand the scale of what we're dealing with. The observable universe, the part of the cosmos we can, in principle, see, has a diameter of about 93 billion light-years. That number alone is almost impossible to imagine. Light, the fastest thing in existence, traveling at about 300,000 kilometers per second, would take 93 billion years to cross it. But instead of trying to picture that directly, let's build it step by step. Inside this vast sphere, there are not just a few galaxies, but hundreds of billions of them. Some estimates suggest there could be up to 2 trillion galaxies, each one a massive system of stars bound together by gravity. 2 trillion galaxies. Already the number feels overwhelming. And inside each of those galaxies are stars. Not a handful, not millions, billions. In our own galaxy, the Milky Way, there are roughly 100 billion stars. Some galaxies are smaller, containing only a few million stars. Others are far larger, holding up to 1 trillion. But if we take a rough average, about 100 billion stars per galaxy, and multiply that by 2 trillion galaxies, we arrive at a number so large it almost loses meaning. Around 200 billion trillion stars. That is a 2 followed by 23 zeros. A number so vast that if you tried to count 1 star per second, it would take you longer than the current age of the universe, just to finish. So at this point, it's tempting to stop and conclude, of course the universe is full. How could it not be? With numbers like these, it feels impossible that space could be anything but crowded. But numbers alone can be deceptive, because quantity is not the same as density. To understand density, we need to go one step further. We need to ask not just how many stars exist, but how much space they actually occupy. Let's begin with something familiar, a star like our Sun. The Sun is enormous by human standards, about 1.4 million kilometers across. If you could somehow hollow it out, you could fit more than 1 million Earths inside. It is a massive, glowing sphere of plasma, dominating the space around it. Now imagine taking that star and measuring its volume. Then imagine doing that for every star in the universe, all 200 billion trillion of them. When scientists perform this calculation, they find something interesting. The total volume occupied by all stars combined is indeed enormous, a number so large that, once again, it stretches the limits of imagination. But now comes the crucial step. We compare that number to the volume of the observable universe itself. And this is where everything changes. Because the observable universe is not just large, it is incomprehensibly large. Its radius is about 46.5 billion light-years. When you convert that into kilometers and then calculate the volume of a sphere that size, you end up with a number so vast that it dwarfs almost anything we've encountered before. And when you divide the total volume of all stars by the total volume of the universe, you get a fraction so small that it barely registers. Stars do not fill even a tiny percentage of space. They do not fill 1/billionth of a percent. They do not fill 1/trillionth of a percent. They occupy less than 1/quadrillionth of a quadrillionth of a quadrillionth of a percent of the universe. A number so small that, for all practical purposes, it is zero. Let that settle in for a moment. All the stars you have ever seen, all the galaxies revealed by telescopes, all the glowing structures that make the universe feel alive, they take up almost none of the space that exists. If you could shrink the entire observable universe down to the size of Earth, compressing everything proportionally, the total volume of all stars combined would be smaller than a single atom. Not a grain of sand, not a drop of water. An atom. And even that comparison might be too generous. The universe is not just empty. it is overwhelmingly, almost completely empty. But the story doesn't end there, because even this calculation is still giving matter too much credit. So far, we've been treating stars as if they are solid objects, as if their entire volume is filled with substance. But that's not actually true. To understand why, we need to go deeper, down to the smallest scales of matter itself. Inside every atom, there is a nucleus at the center, made of protons and neutrons. Around that nucleus, electrons move in a kind of quantum cloud. But the important detail is this: the nucleus is incredibly small compared to the size of the atom. If you imagine an atom as the size of a stadium, the nucleus would be like a tiny grain of sand sitting at the center. Everything else, the vast majority of the atom, is empty space. That means that even the matter inside stars is mostly empty. The particles are packed closely enough to create pressure, heat, and light, but at the fundamental level, the structure is still dominated by space, not substance. So when we say that stars occupy a tiny fraction of the universe, we are already overestimating how much stuff there actually is. Because most of what we call matter isn't solid at all. It's structure. It's energy. It's particles separated by space. Now take that idea and apply it across the entire cosmos. Between atoms, there is space. Between stars, there is vastly more space. Between galaxies, the emptiness becomes almost absolute. And when you combine all of these scales together, from the smallest particles to the largest structures, a pattern emerges. A pattern that is difficult to accept at first. The universe is not built from solid things. It is built from emptiness, with tiny traces of matter scattered within it. And this changes how we should think about everything we've seen so far. Those breathtaking images from Hubble, those dense clusters of galaxies, those glowing bands of stars across the night sky. They are not representative of the universe as a whole. They are exceptions, rare concentrations of matter in a cosmos that is otherwise dominated by nothing. It's like looking at a few scattered islands and assuming the entire planet is land, ignoring the vast oceans that surround them. But in reality, ocean of the universe is far more dominant than any island. And that realization carries a strange emotional weight, because it forces us to confront a universe that is not just large, but sparse, not just vast, but nearly empty. A place where structure is rare, and where most of existence is silent, dark, and without form. And yet, even this is not the deepest layer of the problem. Because everything we have counted so far, all the stars, all the galaxies, all the visible matter, is only what we can detect. It is the part of the universe that interacts with light, the part that reveals itself through observation. But what if that is not the whole story? What if the visible universe is only a small fraction of what actually exists? Because when scientists looked closer, when they began to study how galaxies move, how they rotate, how they interact, they discovered something deeply unsettling. There is more out there than we can see, much more. And it changes everything. Because if the matter we can see is already vanishingly rare, the deeper problem is that most of the universe isn't visible at all. Now that we've stepped back and looked at the numbers, something begins to shift. The universe is no longer just large. It becomes sparse. But numbers alone can feel distant, abstract, difficult to hold in your mind for more than a moment. So instead of thinking about trillions of galaxies or unimaginable volumes, let's bring the scale back down to something we can almost feel. Let's start here, with a single star, our star, the Sun. It sits at the center of our solar system, a massive sphere of glowing plasma dominating everything around it. The Earth orbits at a comfortable distance, about 150 million kilometers away. Even that distance feels enormous. Light from the sun takes about 8 minutes to reach us. Now imagine leaving the sun behind, traveling outward past the orbit of Mars, Jupiter, Saturn, past the icy edge of the solar system where the sun becomes just another bright star in the sky. Where is the next star? Not the next planet, not the next object in our solar system. The next star. The closest one is Proxima Centauri, and it is about 4.2 light-years away. That means if you could travel at the speed of light, faster than anything we can actually build, it would still take more than 4 years to get there. But let's translate that into something more intuitive. If the sun were shrunk down to the size of a grain of sand, about 1 millimeter across, how far away would the nearest star be? It wouldn't be in the same room. It wouldn't be across the street. It would be about 30 kilometers away, roughly 20 miles. Imagine holding a tiny grain of sand in your hand, representing the sun. Then imagine another grain of sand sitting 20 miles away, representing the nearest star. Everything in between is empty. That is the typical spacing between stars in our region of the galaxy. Not crowded, not dense, but separated by vast distances that dwarf the objects themselves. And this is in a galaxy that feels, from the inside, rich with stars. The Milky Way contains around 100 to 200 billion stars, a massive rotating disk stretching across about 100,000 light-years. When we look up at the night sky and see that faint glowing band, we are looking along the dense plane of this galaxy. It feels like a river of light. But even within that river, the stars are scattered, each one isolated in its own region of space, each one surrounded by an ocean of emptiness. Now let's zoom out. Imagine the Milky Way as a whole, a vast island of stars rotating slowly through the darkness, spiral arms stretching outward, clusters of stars forming patterns that take hundreds of millions of years to complete a single rotation. Surely something this large must fill space. Surely a galaxy must feel dense. But now consider its nearest large neighbor, the Andromeda Galaxy. It is the closest galaxy to us that is similar in size to the Milky Way, and it is about 2.5 million light-years away. To put that into perspective, the Milky Way itself is about 100,000 light-years across. That means the distance to Andromeda is roughly 25 times the width of our entire galaxy. If you imagine the Milky Way as a city, Andromeda would not be the next city over. It would be on another continent, separated by an ocean so vast that crossing it would take millions of years, even at the speed of light. Now let's return to our grain of sand analogy. If the Milky Way were reduced to the size of a small coin, then Andromeda would be another coin sitting hundreds of meters away. And between them, almost nothing. A few tiny dwarf galaxies, some faint streams of stars, but mostly empty space. This is what our local group of galaxies looks like, and here's the unsettling part. Our local group is considered a relatively dense region of the universe. We are not in a void. We are not in a particularly empty place. We are in one of the more populated neighborhoods. And yet even here, the distances between major structures are enormous. Now zoom out even further. Beyond our local group, galaxies form clusters. Clusters form superclusters, and these superclusters are connected by long filaments, forming what scientists call the cosmic web, a vast network of structure stretching across hundreds of millions of light years. At first, this sounds like it might finally fill the universe. A web implies connection, density, continuity. But even this structure is mostly empty, because between those filaments are voids, enormous regions where almost nothing exists. These voids are not small gaps. They are some of the largest structures in the universe. Some span hundreds of millions of light years. Some approach 1 billion light years across. Inside them, there are very few galaxies, sometimes only a handful scattered across distances so vast that they barely register. Imagine standing in one of these voids, looking out into space. You would not see a sky filled with galaxies. You would see darkness, almost complete darkness. The nearest large cluster of galaxies might be hundreds of millions of light years away in every direction. There would be no bright band of the Milky Way across your sky, no nearby galaxies glowing faintly in the distance, just a few dim stars belonging to your own isolated system, surrounded by an endless, silent void. This is not science fiction. This is reality. Most of the volume of the universe is made up of these voids, not the galaxies, not the clusters, but the empty regions in between. And those regions are growing. As the universe expands, galaxies move farther apart, structures stretch, voids become larger and emptier over time. The rich regions, the clusters and filaments, hold on to their matter through gravity. But the empty regions become emptier. So what we are seeing today is not a static picture. It is a universe evolving toward greater emptiness, where matter becomes more isolated, where distances grow larger, where the gaps between structures widen beyond anything we can easily imagine. And this leads to a quiet realization. Emptiness is not a side effect of the universe. It is its defining feature. The stars are the exception. The galaxies are the exception. Even the clusters are the exception. What dominates the universe is not matter. It is space. Endless, silent, unoccupied space. And yet, from where we stand, inside a galaxy surrounded by stars, it doesn't feel that way. It feels full, alive, crowded. But that feeling comes from our position. We are inside one of the rare regions where matter has gathered, a small pocket of structure in an otherwise vast and mostly empty cosmos. And from inside that pocket, everything appears closer, brighter, more connected than it truly is. But step outside that perspective, just for a moment, and the illusion fades. You begin to see the universe not as a dense collection of objects, but as a scattering, a few points of light drifting in an ocean of darkness. And that ocean is not calm. It is expanding, stretching, pulling everything apart slowly but relentlessly. Which raises a question that lingers quietly in the background. If emptiness is already the dominant condition of the universe, what happens as time goes on? What happens when the distances grow even larger? When galaxies drift beyond visibility? When the night sky itself begins to fade? But before we can answer that, there is something even more unsettling to confront. Because even after counting stars, measuring distances, and mapping galaxies, something didn't add up. Something was missing. Something that we could not see, but could not ignore. But even after counting stars, gas, and galaxies, scientists realized something was still missing. There is a moment in science when the problem is no longer what we can see, but what we can't. Up until now, The story of the universe has been about emptiness, vast distances, scattered matter, a cosmos where structure is rare and space dominates everything. But in the early 20th century, astronomers began to notice something strange, something that didn't fit. Because even in a universe that is mostly empty, the small amount of matter that does exist should still behave in predictable ways. Gravity should hold things together. Stars should orbit in patterns we can calculate. Galaxies should move according to the mass we can observe. And for a while, everything seemed to follow those rules, until someone looked closer. In the 1930s, a Swiss astronomer named Fritz Zwicky was studying a massive structure known as the Coma Cluster. This is not a single galaxy, but a large group of galaxies bound together by gravity, located hundreds of millions of light years away. Zwicky was interested in how these galaxies moved. Inside a cluster like Coma, each galaxy orbits the center of mass of the cluster, much like planets orbit a star. By measuring how fast these galaxies were moving, Zwicky realized he could estimate how much total mass was required to keep the cluster held together. It was a simple idea. Faster motion means stronger gravity is needed to prevent the system from flying apart. So he measured the speeds. Then he looked at the galaxies themselves, their brightness, their size, and used that to estimate how much mass they contained. And that's when the problem appeared. The galaxies were moving far too fast. Based on the visible matter alone, the cluster should not have been stable. The galaxies should have escaped, drifting away into space long ago. The gravitational pull from the stars and gas we could see simply wasn't enough to hold everything together. It was as if you looked at a spinning system and realized there wasn't enough weight to keep it from breaking apart. Something was missing. Zwicky calculated that the cluster needed hundreds of times more mass than what was visible. Hundreds. Not a small correction, not a rounding error, a massive discrepancy. So he proposed a radical idea. There must be additional matter present, matter that does not emit light, invisible matter. He called it dark matter. At the time, the idea sounded almost absurd. Matter that you cannot see, cannot detect directly, that does not interact with light in any obvious way, and yet still has mass, still exerts gravity, still shapes the motion of entire galaxies? It challenged intuition. It challenged observation. And most scientists didn't accept it. They assumed Zwicky had made a mistake. Maybe his measurements were off. Maybe the galaxies weren't truly bound together. Maybe the laws of gravity behaved differently on such large scales. So the idea lingered, uncertain, unproven. For decades, dark matter remained a possibility, but not a conclusion. And then, in the 1970s, the mystery returned. This time, not in distant clusters of galaxies, but within galaxies themselves. An astronomer named Vera Rubin began studying the rotation of spiral galaxies, systems like our own Milky Way. Her goal was straightforward: measure how fast stars orbit the center of their galaxy at different distances. If you think about our solar system, the pattern is clear. Planets closer to the Sun move faster. Mercury completes an orbit in just 88 days. Earth takes a year. Jupiter takes nearly 12 years. The farther you are from the central mass, the weaker gravity becomes, and the slower your orbit. This is what physics predicts, and it's what astronomers expected to see in galaxies. Stars near the center should move quickly, where most of the mass is concentrated. Stars farther out should move more slowly, as the gravitational pull weakens. But that's not what Rubin found. When she measured the speeds of stars in the outer regions of galaxies, she discovered something astonishing. they weren't slowing down. They were moving just as fast as stars closer to the center. In some cases, even faster. This made no sense, because if the visible matter, the stars and gas we can see, were the only source of gravity, those outer stars should not be able to maintain such high speeds. They should drift away, escaping the galaxy's pull. But they didn't. They stayed in orbit, stable, consistent, as if there were additional mass, extending far beyond the visible edge of the galaxy. Invisible mass. Once again, the same conclusion emerged. There is more matter than we can see. And this time, it wasn't just one cluster. It wasn't just one measurement. It was a pattern, repeated across galaxy after galaxy. Everywhere astronomers looked, the same discrepancy appeared. Visible matter could not account for the observed motion. The numbers didn't add up, and the simplest explanation was dark matter. Not a small correction, not a minor addition, but a dominant component. In fact, when scientists calculated the total mass of galaxies, they found that the visible matter, stars, gas, dust, accounts for only a small fraction, roughly 10 to 15%. The remaining 85 to 90% is something else, something invisible. Something that does not emit light, does not absorb light, and does not interact with electromagnetic radiation in any meaningful way. And yet, it has mass. It exerts gravity. It shapes the structure of the universe. This was the moment when the story of the cosmos changed, because until now, emptiness had been the central theme. The idea that space is vast and mostly unoccupied, that matter is rare and scattered. But dark matter introduced something new. The universe wasn't just empty. It was hidden, filled with something we could not see, something that surrounds galaxies, extends far beyond their visible edges, and holds them together like an invisible framework. Imagine looking at a city at night. You see the lights of buildings, the glow of streets, the movement of cars. But beneath that visible layer is an entire infrastructure, foundations, steel beams, underground systems that you cannot see, but that make the city possible. Dark matter is like that infrastructure, except on a cosmic scale. Every galaxy is embedded in a vast halo of dark matter, stretching far beyond the stars we can observe. This halo provides the gravitational pull needed to hold the galaxy together, to keep its stars in orbit, to shape its structure over billions of years. Without it, galaxies as we know them might not exist at all. And yet, we cannot see it. We cannot touch it. We can only infer its presence through its effects. This is what makes dark matter so unsettling. It is not just a missing piece. It is the majority, the dominant form of matter in the universe, and we don't know what it is. It could be made of new particles that we have never detected. It could behave in ways that are completely outside our current understanding of physics. It could be something entirely unexpected. For decades, scientists have tried to find it directly. They have built detectors deep underground, shielded from radiation, waiting for the faintest interaction between dark matter and normal matter. They have used powerful particle accelerators, smashing particles together in the hope of creating something new. They have searched the skies for subtle gravitational effects that might reveal its nature. So far, nothing conclusive. We know it's there. We can measure its influence, but we cannot see it. And this creates a strange tension, because earlier we discovered that the universe is mostly empty, that stars and galaxies occupy almost none of its volume. But now, we are forced to accept something even more unsettling. Most of the matter that does exist is invisible. So not only is space overwhelmingly empty, but even the parts that aren't empty are dominated by something we cannot perceive. The universe is not just vast and sparse, it is fundamentally mysterious. And as this realization settles in, the picture becomes even more complex, because dark matter is only part of the story. There is another force, another discovery, one that doesn't just add hidden mass to the universe, but actively changes its fate. And if dark matter revealed that the universe is held together by something invisible, what comes next will reveal that it is also being pulled apart. The universe wasn't just empty. It was haunted by mass we couldn't see. There is something quietly unsettling about dark matter. Not just because we cannot see it, but because once you accept that it exists, the entire picture of the universe begins to change. Up until now, it was easy to imagine that the visible universe, the stars, the galaxies, the glowing clouds of gas, was the main structure of reality. Even if space was mostly empty, at least what we could see felt like the foundation, the solid part, the part that mattered. But dark matter forces us to reconsider that idea, because it turns out that the visible universe is not the foundation at all. It is more like a surface, a thin, glowing layer floating on top of something much deeper. To understand this, we need to stop thinking about dark matter as just extra mass and start thinking about what it actually does, what role it plays, what kind of universe it creates. Imagine the early universe shortly after the Big Bang. At that time, everything was hot, dense, and relatively smooth. Matter was spread out across space, with only tiny variations in density, slightly denser regions here, slightly emptier regions there. These small fluctuations were the seeds of everything that would come later. But turning those small differences into galaxies is not easy, because normal matter, the kind we are made of, does not behave in a simple way. It interacts with light. As clouds of gas begin to collapse under gravity, they heat up, and as they heat up, they emit radiation. That radiation pushes outward, resisting further collapse. It's like trying to compress a glowing gas that keeps pushing back against you. Gravity pulls inward, radiation pushes outward, and the result is a delicate balance. Too much pressure, and the gas spreads out again. Too little, and it collapses too quickly on its own. Normal matter struggles to form large structures efficiently. It resists compression. It fights against its own collapse. So if the universe were made only of normal matter, the formation of galaxies might have been slow, inefficient, or perhaps even impossible in the way we see them today. This is where dark matter changes everything. Because dark matter does not interact with light. It does not emit radiation. It does not absorb it. It does not feel that outward pressure. It simply responds to gravity. And because of that, it can do something normal matter cannot. It can collapse freely. In the early universe, while normal matter was still interacting with radiation, dark matter began to clump together. Slowly, quietly, guided only by gravity, it formed structures, large, invisible clouds of mass. These were the first building blocks of the cosmic web. Not stars, not galaxies, but dark matter halos. Vast, roughly spherical regions where dark matter had gathered, creating deep gravitational wells in the fabric of space. You can think of these halos as valleys in an otherwise flat landscape, regions where gravity is stronger, pulling anything nearby inward. And once these structures formed, something remarkable happened. Normal matter began to fall into them. Hydrogen and helium gas, drifting through space, was pulled into these dark matter wells. As it fell inward, it became denser. As it became denser, it began to cool, collapse further, and eventually form stars. In other words, galaxies did not form on their own. They formed inside dark matter. Every galaxy you have ever seen, every spiral arm, every glowing core, every cluster of stars, is sitting at the center of a much larger, invisible structure, a dark matter halo. And these halos are enormous. Take the Milky Way as an example. The visible part of our galaxy, the stars, the gas, the glowing disk, is about 100,000 light-years across. But the dark matter halo surrounding it extends much farther, at least 600,000 light-years in diameter, possibly more. That means the vast majority of our galaxy is not visible. It is an invisible structure surrounding the part we can see, and it contains most of the mass. Roughly 85 to 90% of the Milky Way's mass is not in stars or gas. It is in dark matter. So when you look at an image of our galaxy, you are not seeing the whole thing. You are seeing a small, luminous core embedded within something far larger, like a candle flame floating inside an invisible sphere. And this is not unique to the Milky Way. Every galaxy we observe appears to have this same structure. A visible component, stars, gas, dust, surrounded by a much larger dark matter halo. The visible galaxy is just the part that shines. The dark matter is the part that shapes it. And this has profound implications, because it means that the structure of the universe is not defined by what we can see. It is defined by what we cannot. The cosmic web, the vast network of filaments and clusters stretching across the universe, is primarily a structure of dark matter. The galaxies trace out this web, lighting up the densest regions like sparks along invisible threads. But the threads themselves are dark. Without dark matter, those threads would not exist. Without those threads, galaxies would not form in the same way. Without galaxies, there would be no stars, no planets, no chemistry complex enough to create life. In a very real sense, dark matter made everything we know possible, and yet it remains completely hidden. It does not shine. It does not glow. It does not reflect light. It passes through normal matter almost without interaction. Right now, as you sit here listening, billions of dark matter particles may be passing through your body every second. You do not feel them. You cannot detect them. To you, they might as well not exist. And yet, on cosmic scales, they dominate. This creates a strange duality. On human scales, dark matter is irrelevant, invisible, untouchable, silent. But on cosmic scales, it is everything. It determines how galaxies rotate. It controls how structures form. It shapes the evolution of the universe itself. And we only know it exists because of its gravitational effects. We see how stars move. We measure how galaxies rotate. We observe how light bends around massive structures. And in every case, the same conclusion emerges. There is more mass than we can see. And that mass is not evenly distributed. It forms halos. It forms structures. It builds the invisible framework of the cosmos. This is why the idea of dark matter is so powerful. Not because it adds something new to the universe, but because it redefines everything we thought we understood. The visible universe, the part filled with stars and light, is not the primary structure. It is a secondary effect, a consequence of something deeper, something unseen, something that does not interact with light, but controls everything that does. And once you begin to see the universe this way, the night sky changes again. Those stars you see, they are not floating freely in space. They are anchored, held in place by an invisible structure that surrounds them, extends far beyond them, and binds them together. Every galaxy is like a lantern, and dark matter is the vast, invisible architecture that holds all those lanterns in place. So when you look up at the sky, you are not seeing the universe itself. You are seeing the illuminated parts of a much larger, hidden system. A system that exists whether we can see it or not. A system that dominates the mass of the cosmos. And yet, we still don't know what it is made of. This is the deeper mystery. We understand what dark matter does. We can describe its effects with remarkable precision. But its true nature remains unknown. It could be a new kind of particle. It could be something entirely outside our current theories. It could be a clue pointing toward a deeper understanding of physics itself. And until we solve that mystery, our picture of the universe will remain incomplete. Because we are trying to understand a structure we can only partially see, a system where most of the mass is invisible, a universe where the foundation is hidden from view. And that realization leads to a quiet, almost unsettling conclusion. The visible universe isn't the whole story. Not even close. So the visible universe isn't the whole structure. It's just the illuminated skin of something much larger and unseen. There is a strange kind of certainty in science. We are often taught that science is about answers, about clarity, about turning the unknown into something understood. But sometimes, the deeper we look, the more precise our questions become, and the less certain our answers feel. Dark matter is one of those moments. We know it is there. We can measure its influence across the universe. We can see how galaxies rotate, how clusters hold together, how light bends as it passes through invisible mass. Its presence is written into the structure of the cosmos itself, like a fingerprint pressed into space. And yet, when we ask the simplest question, what is it made of? The answer becomes silent. It is one of the most profound mysteries in modern science, because dark matter is not just a missing detail. It is most of the matter in the universe, and we don't know what it is. So how do scientists approach something like this? They begin with possibilities, not guesses, but carefully constructed ideas, hypotheses grounded in physics, tested against observation, refined over time. Each one attempts to explain how something can have mass, shape galaxies, and yet remain completely invisible. One of the earliest and most compelling ideas was something called WIMPs, weakly interacting massive particles. The name itself tells a story. These would be particles that have mass, so they can create gravity, but interact only very weakly with normal matter. They would not emit light. They would not absorb it. They would pass through atoms almost as if nothing were there. much like dark matter appears to do. For many years, WIMPs seemed like the perfect answer. In the early universe, conditions were extremely hot and dense. Under those conditions, particles like WIMPs could have formed naturally, just like the particles that make up atoms today. And as the universe expanded and cooled, these particles would remain, drifting through space, forming the invisible halos we observe around galaxies. Even more intriguing, calculations showed that if WIMPs existed with certain properties, they would naturally produce the exact amount of dark matter we observe today. This coincidence was so striking that it became known as the WIMP miracle. It felt like a clue, as if the universe were pointing us toward the answer. So scientists began to search. Deep underground, far from cosmic radiation, they built sensitive detectors. Vast chambers filled with ultra-pure materials designed to catch the faintest possible interaction between a dark matter particle and a normal atom. The idea was simple. If WIMPs pass through everything, then occasionally, very rarely, they might collide with something. And if we were patient enough, we might detect it. At the same time, particle accelerators like the Large Hadron Collider began probing the fundamental structure of matter. By smashing particles together at incredibly high energies, scientists hoped to create dark matter particles directly, observing their effects through missing energy, signs that something invisible had been produced and escaped detection. Years passed. Experiments became more precise. Detectors became more sensitive. But the result remained the same. Nothing conclusive. Hints appeared from time to time, small signals that seemed promising, only to fade under closer scrutiny. The WIMP remained a possibility, but no longer a certainty. And so the mystery deepened. If dark matter is not made of WIMPs, then what else could it be? Another idea emerged. Axions. Unlike WIMPs, axions would be incredibly light, far lighter than the particles that make up atoms. So light, in fact, that they would behave less like individual particles and more like a kind of subtle field spread across space. At first, axions were not proposed to explain dark matter at all. They were introduced to solve a completely different problem in particle physics, but over time, scientists realized that if axions exist in large enough numbers, they could account for the missing mass of the universe. Instead of a few heavy particles, dark matter could be made of an enormous number of extremely light ones, like a fog filling the cosmos, invisible, pervasive, almost impossible to detect directly. Experiments began to search for axions as well, sensitive instruments designed to detect tiny conversions between axions and photons, particles of light, under very specific conditions. So far, no confirmed detection. The fog, if it exists, remains hidden. Then there is a more dramatic possibility. Primordial black holes. These are not the black holes formed from dying stars, but objects that might have formed in the very early universe, when density fluctuations were extreme enough to collapse regions of space directly into black holes. If enough of these primordial black holes formed, and if they exist in the right size range, they could account for dark matter. They would be invisible unless actively consuming matter. They would have mass. They would exert gravity. They would fit the profile. But this idea comes with challenges. Black holes, even small ones, leave subtle signatures. They bend light in characteristic ways. They create gravitational lensing effects that we can observe. And so far, the number of such effects we see does not seem to match what would be required if primordial black holes made up all of dark matter. So once again, the answer remains uncertain. And then there is an even more radical idea. What if dark matter doesn't exist at all? What if the problem is not missing matter, but our understanding of gravity? Some scientists have proposed that the laws of gravity might behave differently on very large scales, that in the weak gravitational environments of galaxies and clusters, gravity might not follow the simple rules we expect. This idea is known as modified gravity. Instead of adding unseen mass, it changes the rules of the game. In some cases, modified gravity can explain certain observations, like the rotation curves of galaxies. But when tested against the full range of cosmic data, clusters, gravitational lensing, the cosmic microwave background, it struggles to provide a complete picture. Dark matter, for all its mystery, still explains more consistently, more completely. And so, despite all these possibilities, the central truth remains unchanged. We know what dark matter does. We do not know what it is. It shapes galaxies. It binds clusters. It forms the invisible scaffolding of the universe. And yet, it refuses to reveal its identity. This creates a strange tension at the heart of modern cosmology. We have mapped the large-scale structure of the universe with incredible precision. We can simulate its evolution from the earliest moments after the Big Bang to the present day. We can predict how galaxies should form, how clusters should behave, how light should travel through space, and all of it depends on something we have never directly detected. It is like solving a puzzle where one of the largest pieces is missing, and yet the image still makes sense. Or like listening to a symphony where you cannot hear one of the instruments, but you can feel its presence in the way the music moves. Dark matter is that missing instrument, always there, never seen, and perhaps most unsettling of all, it is everywhere. Right now, as you sit here, the Earth is moving through a vast halo of dark matter. The solar system is immersed in it. The galaxy is surrounded by it. Billions of particles, whatever they may be, are passing through your body every second. They do not interact with you. They do not leave a trace, but they are there. A silent presence woven into the fabric of reality. And this leads to a deeper realization. The universe is not just empty. It is filled with something we cannot perceive, something that dominates its structure, something that shapes its evolution. And we are only beginning to understand it. This is not the end of the story. It is the beginning of a new one. Because once you accept that most of the matter in the universe is invisible, the next question becomes unavoidable. If dark matter holds the universe together, what could possibly tear it apart? And just when it seems the invisible mass is the strangest thing in the cosmos, the universe reveals an even darker force. There are discoveries that expand our understanding, and then there are discoveries that break it. Up to this point, the universe had already become strange. We learned that it is mostly empty, that most of its matter is invisible, that galaxies are held together by something we cannot see. But even with all of that, there was still a sense of stability. Gravity was the anchor. It was the force that built structure, that pulled matter together, that shaped galaxies, clusters, and the cosmic web itself. Even in an expanding universe, gravity was expected to be the ultimate counterbalance. It might slow the expansion over time. It might even reverse it someday, pulling everything back together in a final collapse. That was the expectation. That was the story. And for decades, scientists worked to measure exactly how this cosmic tug-of-war was playing out. Was gravity strong enough to stop the expansion? Would the universe eventually collapse back into itself, or would it expand forever, slowly coasting outward as gravity gradually weakened its motion? To answer these questions, astronomers needed a way to measure distances across the universe with extreme precision. Not just nearby distances, but distances spanning billions of light years. And for that, they turned to something extraordinary. A specific type of exploding star, a Type 1a supernova. These are not ordinary explosions. They occur in binary star systems, where one of the stars is a white dwarf, the dense, compact core left behind after a star like our Sun dies. Over time, this white dwarf pulls matter from its companion star, slowly gaining mass. And then, at a very precise point, something dramatic happens. When the white dwarf reaches a critical mass, about 1.4 times the mass of the Sun, it becomes unstable. Nuclear reactions ignite in a runaway process, and the entire star explodes in a matter of seconds. The result is one of the most powerful events in the universe. A flash of light so bright that for a brief moment, it can outshine an entire galaxy. But what makes these explosions truly valuable is not just their brightness, it's their consistency. Because every Type 1a supernova explodes at nearly the same mass, they all produce roughly the same peak brightness. That means they can be used as what astronomers call standard candles, objects whose true brightness is known. And if you know how bright something truly is, and you measure how bright it appears from Earth, you can calculate its distance. Dimmer means farther away. Brighter means closer. It's a simple idea, but incredibly powerful. Using these cosmic beacons, astronomers began mapping the expansion of the universe across time. Two independent teams took on this challenge in the 1990s. The Supernova Cosmology Project and the High-Z Supernova Search Team. Working separately, using different methods, they set out to measure how fast the universe was expanding at different points in its history. They searched for distant supernovas, explosions that occurred billions of years ago, and compared their distances to their redshifts. Redshift is the stretching of light caused by the expansion of space. The farther away a galaxy is, the faster it appears to be moving away from us, and the more its light is shifted toward the red end of the spectrum. By combining distance and redshift, scientists could reconstruct the expansion history of the universe. And based on everything they understood about gravity, they expected to see a slowing. After the Big Bang, the universe expanded rapidly. But over time, gravity, pulling everything together, should have gradually reduced that expansion rate. The question was not whether the expansion was slowing, it was how much. But when the data came in, something didn't make sense. The distant supernovas were dimmer than expected. Not dramatically, but consistently. And dimmer meant farther away than they should have been if the universe's expansion had been slowing down. It was a small discrepancy at first, easy to doubt, easy to question. Maybe there was an error in the measurements. Maybe dust in space was dimming the light. Maybe something else was interfering with the observations. But both teams saw the same result, independently. And as more data was collected, the pattern became clearer, stronger, impossible to ignore. The universe was not slowing down. It was speeding up. Expansion was accelerating. This was not just unexpected, it was shocking, because it meant that gravity, the force that builds galaxies, that binds stars, that shapes the universe, was losing. something else was at work, something pushing space apart, something acting against gravity on the largest scales. This force was given a name: dark energy. But, like dark matter, the name does not explain what it is. It only describes what we don't understand. Dark energy is not something we can see. It does not form structures. It does not clump. It does not create galaxies or stars. Instead, it does the opposite. It drives space itself to expand faster and faster over time. To understand how strange this is, imagine the universe as a stretching fabric. Galaxies are like dots drawn on that fabric. As the fabric expands, the dots move away from each other. This is the basic idea behind cosmic expansion. But now imagine that the fabric is not just stretching, it is accelerating. Every second, it expands faster than the second before. The distances between galaxies are not just increasing, they are increasing at an increasing rate. And the larger the distance, the stronger this effect becomes. On small scales, gravity still dominates. Galaxies hold together. Stars remain bound. The solar system is unaffected. But on the largest scales, dark energy takes over. It overwhelms gravity. It pushes galaxies apart. It stretches the cosmic web. It enlarges the voids. And over time, it will isolate every structure in the universe. This changes everything. Because now, emptiness is not just a passive condition, it is an active process. The universe is not simply empty because matter is rare. It is becoming more empty over time, and the implications are staggering. In the distant future, galaxies beyond our local group will move so far away that their light will never reach us again. They will fade beyond the observable universe, not because they disappear, but because space itself expands too quickly for their light to cross the growing distance. The night sky will grow darker, quieter, more isolated. Eventually, observers in the far future may see only their own galaxy, surrounded by darkness, with no evidence of the vast universe that once existed. The cosmic web will dissolve into isolated islands of matter, drifting endlessly apart. And this process has already begun. Right now, as you listen to this, the universe is expanding, faster than it was yesterday, faster than it was 1 billion years ago. And it will continue to accelerate, driven by something we cannot see, something we barely understand. Dark energy is not just another missing piece. It is the dominant component of the universe. Roughly 68% of everything, more than dark matter, more than all visible matter combined. Which means that most of the universe is not just invisible. It is actively pushing everything apart. And this creates a profound shift in how we understand reality. Because for the first time, we are not just observing a universe that exists. We are observing a universe that is evolving toward isolation, toward emptiness, toward a future where structure becomes increasingly rare. And this brings us back to the central idea of this journey. The universe is empty, not by accident, not by coincidence, but by design of its fundamental forces. Dark matter built structure. It pulled matter together, formed galaxies, created the conditions for stars and life. But dark energy is undoing that work, slowly, relentlessly, stretching everything apart, and leaving behind a cosmos that grows colder, darker, and more silent with time. Which raises a question that lingers in the background. If dark matter gave the universe its structure, and dark energy is taking it away, what does that mean for the future of everything we see? Dark matter built structure. Dark energy is erasing it. There is a quiet shift that happens once you accept dark energy. At first, it feels like just another discovery, another missing piece in a universe already filled with mysteries. But the deeper you think about it, the more unsettling it becomes. Because dark energy is not just something that exists, it is something that acts. It changes the future of the universe. It changes the meaning of emptiness itself. Up until now, emptiness has felt like a condition, a result of vast distances and scattered matter, a kind of passive backdrop where galaxies drift and stars shine. But dark energy turns that idea on its head, because emptiness is not just sitting there, it is growing. To understand this, we need to look at something that sounds simple but carries profound consequences. The idea that empty space itself might have energy. It feels counterintuitive. When we think of empty space, we imagine nothing. No matter, no light, no structure, just a void. But in modern physics, even perfect vacuum is not truly empty. It has properties. It has structure at the quantum level. And most importantly, it may have energy. This idea is often called vacuum energy, or, in another form, the cosmological constant, a term first introduced by Albert Einstein over a century ago. Einstein originally added it to his equations for a very specific reason. At the time, scientists believed the universe was static, unchanging, eternal. But Einstein's equations suggested that gravity would cause everything to collapse inward over time. To counteract that collapse, he introduced a small repulsive force, a constant energy embedded in space itself, pushing outward just enough to balance gravity. Later, when the expansion of the universe was discovered, Einstein reportedly called this his greatest mistake. He removed the constant, but decades later, the universe brought it back. Not as a correction, but as a necessity. Because the accelerating expansion we observe today behaves almost exactly like what Einstein once imagined. A constant energy built into space. A force that does not weaken as the universe grows. And that is the key difference. Normal matter, everything we can see, becomes more diluted as space expands. Galaxies move farther apart. The same amount of matter is spread across a larger volume, making its average density lower over time. Dark matter behaves similarly. It clumps into structures, but on the largest scales, its influence weakens as distances grow. But dark energy does not dilute. If it is truly a property of space itself, then as space expands, more of it comes into existence. More space means more dark energy, and more dark energy means stronger acceleration. This creates a feedback loop. Expansion creates space. Space contains energy. That energy drives more expansion. And so the process continues, faster and faster. At first, this effect was small. In the early universe, matter dominated. Gravity shaped structure, pulled gas together, formed stars and galaxies. Dark energy was present, but its influence was weak compared to the density of matter. But as the universe expanded, something changed. Matter thinned out. Dark energy did not. Over billions of years, the balance shifted, until eventually, dark energy became the dominant force in the universe. Today, when scientists measure the total content of the cosmos, they find something astonishing. Only about 5% is normal matter, the kind that forms stars, planets, and everything we are familiar with. About 27% is dark matter, invisible but detectable through its gravitational effects. And the remaining 68% is dark energy, the force driving the acceleration of the universe. Think about that for a moment. 95% of the universe is made of things we do not fully understand. Only 5% is the visible world we experience. Everything we have ever seen, touched, or studied directly is a tiny fraction of what actually exists. And most of the rest is not just unknown, it is actively shaping the fate of the cosmos. This is where the emotional weight of the story begins to settle in. Because dark energy is not just another component, it is winning. On the largest scales, it is overpowering gravity, and that means structure is losing. Galaxies that are not gravitationally bound to us are already moving away, carried by the expansion of space. Over time, they will move faster and faster, eventually crossing a boundary where their light can no longer reach us. They will not disappear, but from our perspective, they will fade into darkness, beyond the observable universe. One by one, distant galaxies will vanish. The rich tapestry of the cosmos, the countless structures revealed by telescopes, will slowly unravel. What remains will be smaller, more isolated, more alone. And this is not something that will happen suddenly. It is already happening. Right now, the universe is expanding at an accelerating rate. The distances between galaxy clusters are growing. The cosmic web is stretching. Voids are becoming larger. Emptiness is increasing. Which means that the universe we observe today is not a permanent state. It is a moment, a temporary phase in a much longer story. We live at a time when galaxies are still visible, when the night sky still contains evidence of a vast and interconnected cosmos. But this window will not last forever. In the distant future, observers, if any exist, may not see the same universe we see today. They may look out into space and find only their own galaxy, surrounded by darkness, with no visible trace of the billions of galaxies that once filled the sky. They may have no way of knowing that the universe was ever anything more than what they can observe. The expansion will have erased the evidence. Dark energy will have hidden the past. And this leads to a deeply philosophical realization. We are living in a special time. Not special because we are central, not special because we are important, but special because we can still see. We can still observe the large-scale structure of the universe. We can still detect the cosmic microwave background, the faint afterglow of the Big Bang. We can still measure the expansion and understand its history. We exist in a narrow window where the universe is both structured and observable. Before, it was too hot and dense. After, it will be too empty and isolated. And in between, there is now, a brief moment when the universe reveals itself. But even in this moment, the trend is clear. Structure is fading. Distances are growing. The balance is shifting. And the emptiness that once seemed like a passive feature is becoming the dominant outcome. The universe is not just empty. It is becoming emptier. And there is something quietly unsettling about that, because it suggests that everything we see, the galaxies, the stars, the clusters, are temporary. They are not the final state of the cosmos. They are part of a process that is moving towards something simpler, something quieter, something darker. A universe where matter is isolated, where light is rare, where the vast majority of space contains almost nothing at all. And yet, this is not chaos. It is not random. It is the result of fundamental laws playing out over time. Dark matter built the structure. Dark energy is dissolving it. And in that tension, we see the true nature of the universe. Not static, not balanced, but evolving, slowly moving toward a state where emptiness dominates everything. And nowhere is that process more visible than in the largest structures of all. And nowhere is the victory of emptiness more visible than in the largest structures of all. If you could step far enough away from everything you know, the universe would not look like a collection of stars. It would look like a web. A vast, delicate structure stretching across unimaginable distances. Filaments of galaxies forming long, thread-like bridges. Clusters gathering at the intersections like glowing knots where gravity has pulled matter into dense concentrations. Sheets of galaxies spreading across space like cosmic walls. And between them, nothing. Not small gaps, not thin pockets of emptiness, but enormous regions where almost nothing exists at all. These are the cosmic voids, and they are not rare. They are not unusual. They are the dominant feature of the universe. For a long time, astronomers assumed that galaxies were scattered more or less randomly through space. But as technology improved, they began mapping not just where galaxies appear in the sky, but how far away they are. By measuring redshift, they could build three-dimensional maps of the cosmos, placing each galaxy at its true position in space. And when those maps began to take shape, a pattern emerged. Not chaos, not randomness, but structure. Galaxies were not evenly distributed. They were arranged along filaments, forming a vast cosmic web. Where these filaments intersected, clusters formed, dense regions filled with hundreds or even thousands of galaxies bound together by gravity. But what stood out most was not the structure itself. It was what lay between. The voids. Immense, spherical regions where galaxies were almost entirely absent. At first, these voids were surprising. Then they became unavoidable. Because everywhere astronomers looked, they found them. The universe, it turned out, is not mostly filled with galaxies. It is mostly filled with emptiness, organized into vast, expanding regions. One of the most striking examples is the Boötes void, discovered in the early 1980s. This region is so large that it challenges comprehension. It spans roughly 330 million light-years across. To put that into perspective, our Milky Way galaxy is about 100,000 light-years wide. That means the Boötes void is more than 3,000 times larger than our galaxy. And yet, within this enormous volume, there are almost no galaxies. A typical region of that size might contain around 10,000 galaxies. The Boötes void contains only about 60. 60. Scattered across a volume so vast that each one is almost completely isolated. It is not perfectly empty, but it is close as the universe allows. Imagine standing in a galaxy at the center of that void, looking out into space. What would you see? Not the rich sky we know, not the Milky Way stretching across the darkness, not neighboring galaxies glowing faintly at the edge of visibility. You would see almost nothing. Your own galaxy might be small and dim, Around you, there would be only a few scattered stars visible to the naked eye. And beyond that, darkness. The nearest significant galaxy clusters would be hundreds of millions of light-years away in every direction. Even with powerful telescopes, the sky would remain sparse, lonely, almost empty. A civilization living in such a place might never realize the true scale of the universe. They might believe they exist in a small, isolated cosmos, with little evidence of the vast structures beyond their reach. They might never see the cosmic web, never detect the clusters, never understand that their emptiness is only local. Because the universe does not distribute its matter evenly, it concentrates it, leaving behind regions where almost nothing remains. And this pattern repeats everywhere. The Bootes void is not unique. There are many others, some even larger. The Eridanus supervoid, for example, stretches nearly 1 billion light-years across, a region so vast that even light passing through it appears slightly altered. Photons lose energy as they travel across its underdense expanse, leaving subtle imprints in the cosmic microwave background, the faint afterglow of the Big Bang. There is also the local void, much closer to us, extending tens of millions of light-years from our position in the universe. We are not inside it, but we are near its edge, looking into its emptiness. And even that nearby void is immense. Compared to human scales, it is beyond comprehension. But what matters is not just their size, it is their dominance. When astronomers calculate the total volume of the universe, they find that most of it is made up of these voids. Not galaxies, not clusters, not filaments, voids. The structures we see, the glowing galaxies, the dense clusters, are just the thin outlines of a much larger pattern, like foam on the surface of an ocean, or the walls of bubbles in a vast, expanding space. The true substance of the universe is not the walls, it is the emptiness inside. And this emptiness is not static. It is growing. As dark energy accelerates the expansion of the universe, matter is pulled away from low-density regions and drawn toward denser ones. Filaments become more pronounced, clusters grow more concentrated, and voids expand. They stretch outward, becoming larger and emptier over time. In these regions, there is less gravity to slow the expansion, less matter to hold things together. So space expands faster there than in denser regions. The result is a universe where the rich regions become richer and the empty regions become emptier. This is not just a pattern, it is a process, a long-term evolution toward greater isolation. And inside these voids, conditions are different. The few galaxies that do exist there are often small, dim, and quiet. They are called void galaxies. They contain less gas, form fewer stars, and evolve more slowly than galaxies in denser environments. Without frequent interactions or collisions, they remain relatively unchanged for billions of years. They are like cosmic fossils, preserved in isolation. But that isolation comes at a cost. They are alone, drifting in vast regions of space where encounters are rare, where the night sky is dark, and where the surrounding universe feels distant and unreachable. And as time goes on, that isolation will only deepen, because the expansion of the universe does not treat all regions equally. Voids grow faster. They stretch more rapidly. They dominate more of the total volume, until eventually they become the defining feature of the cosmos. This is the endpoint toward which the universe is moving, a place where matter is concentrated into isolated pockets, separated by distances so vast that communication, travel, and even observation become impossible. A place where most of space contains almost nothing at all. And this brings us to a realization that is both simple and deeply unsettling. Emptiness is not evenly spread. It is structured, organized, dominant. The universe is not just empty in a general sense. It is filled with vast regions where structure has almost completely vanished. Places where the universe has, in a way, given up. Where gravity has lost its hold. Where matter has been pulled away, leaving behind silence, darkness, and distance. And perhaps the most unsettling thought of all is this: we are not in one of those places. We are in a relatively dense region, a small pocket where galaxies are still close enough to see, where the night sky still holds structure, where the universe still feels connected. But that is not the norm. It is the exception. And as the universe continues to evolve, even our region will begin to resemble those voids. Galaxies will drift away. Distances will grow. The sky will grow darker. The connections we see today will slowly disappear, until eventually, emptiness becomes almost absolute. The universe is not merely empty now, it is becoming emptier. And in that realization, there is a quiet sense of inevitability. A sense that what we see today is temporary, a fleeting arrangement of matter in a cosmos that is slowly, steadily, moving towards silence. But if that is where the universe is going, what does that mean for us? What does it mean to exist in a universe where emptiness is not just the background, but the future? And what does it say about the brief moment in which we are able to see it all? The universe is not merely empty now, it is becoming emptier. There is a quiet truth that emerges when you follow this story all the way to its edge. The universe is not what it first appeared to be. It is not dense. It is not full. It is not even stable in the way we once imagined. It is vast, sparse, and slowly unraveling. And yet, here we are, aware of it. For most of cosmic history, there was nothing like us. In the beginning, the universe was too hot, too chaotic for structure to exist. Matter had not yet gathered. Stars had not yet formed. There were no galaxies, no planets, no chemistry complex enough to build life. Just a hot, expanding sea of particles and radiation. Then, over time, something remarkable happened. Dark matter formed the first scaffolding. Gravity pulled gas into those invisible structures. The first stars ignited, lighting up the darkness. Galaxies formed, grew, merged, and evolved. Heavy elements were forged inside stars and scattered across space by explosions. Slowly, patiently, the universe built complexity from simplicity, from emptiness. And within a few rare regions, tiny pockets scattered across an otherwise silent cosmos, conditions became just right. Atoms formed molecules. Molecules formed chemistry. Chemistry formed biology. And eventually, consciousness. The ability not just to exist, but to observe, to question, to understand, to look up at the night sky and wonder what it all means. This is not a small thing. In a universe where almost everything is empty, the existence of something that can think about that emptiness is extraordinary. But here's what makes it even more profound. We exist at a very specific moment in time, a narrow window between two extremes. In the early universe, there was too little structure. In the far future, there will be too much emptiness. But right now, there is balance. Galaxies are still visible across vast distances. The cosmic web still connects structures across millions of light years. The The night sky still contains evidence of a universe rich with history and complexity. We can see the past. We can measure the expansion. We can detect the faint glow of the Big Bang itself. This moment, right now, is one of the few times in the entire history of the universe when such observations are even possible. It will not last. As dark energy continues its slow work, galaxies beyond our local group will drift farther and farther away. Their light will stretch, fade, and eventually disappear from view. The observable universe will shrink, not in size, but in what can be seen within it. Future observers, billions or trillions of years from now, may look out into space and see only their own galaxy. No distant clusters, no cosmic web, no evidence of the vast universe that once existed. To them, the cosmos may appear small, lonely, almost empty. They may never know what was lost, and that raises a quiet, almost haunting question. What does it mean that we can see it now? What does it mean that we exist in this brief moment when the universe is both structured and observable? It is tempting to search for significance, to ask whether this moment was meant for us. But the universe does not seem to operate that way. It is not centered on us. It was not designed for us. It does not pause or adjust for our existence. And yet, here we are. Not because the universe needed us, but because, in a few rare places, under very specific conditions, it became possible. That rarity is important, because structure itself is rare. Galaxies are rare. Stars are rare. Planets are rare. And the chain of events required to produce life, complex, conscious life, is even rarer. It requires the right elements, the right environment, the right stability over long periods of time. It requires a delicate balance that is easily disrupted. And all of that exists within a universe that is overwhelmingly empty. Which means that we are not just small in scale, we are rare in occurrence. We are part of a thin layer of complexity spread across a vast, mostly silent cosmos. And yet, within that thin layer, something remarkable has happened. The universe has become aware of itself. Through us. Through countless minds across a small planet orbiting an ordinary star in an unremarkable galaxy. The universe has developed the ability to observe its own structure, to measure its own expansion, to question its own nature. And perhaps that is where meaning begins to emerge. Not in being central, not in being important, but in being aware. Because awareness is not guaranteed. It is not a necessary outcome of the universe. It is a rare phenomenon that arises only under very specific conditions. Conditions that exist in very few places for a limited time. And that time is passing. The universe is not moving toward greater complexity. It is moving toward simplicity, toward isolation, toward emptiness. Stars will eventually burn out. Galaxies will fade. Black holes will slowly evaporate. And over unimaginable stretches of time, the universe will approach a state where almost nothing happens, where energy is evenly spread, where structure is gone, where the cosmos becomes quiet, cold, and still. This is not speculation. It is the natural consequence of the laws we observe, the direction in which everything is moving. And against that backdrop, this moment stands out. A brief period where structure exists, where light fills the sky, where galaxies are still visible, where life can emerge, where consciousness can reflect on all of it. It is easy to feel small in a universe like this, to feel insignificant in the face of such scale and emptiness. But there is another way to see it, because rarity has its own kind of significance. A single spark in darkness is not less meaningful because it is small. If anything, its rarity makes it more remarkable. The same is true here. We are not the center of the universe, but we are part of something rare. A moment when matter has organized itself in such a way that it can look outward and understand, that it can ask questions about its own existence, that it can trace its origins back to the first moments of the cosmos, and that it can imagine the future, even when that future leads towards silence. There is something deeply human about that, to stand in a universe that is mostly empty and still choose to explore it, to understand it, to find meaning within it, not because it was given to us, but because we are capable of creating it. And perhaps that is the final shift in perspective. The universe does not need to be full to be meaningful. It does not need to be centered around us. It does not need to be permanent. Because meaning does not come from the structure of the cosmos. It comes from the awareness within it, from the ability to observe, to reflect, to understand. In a universe where almost everything is nothing, the fact that something can look back and understand the emptiness may be the rarest thing of all. And perhaps that is enough.